so we need a better model. And we have the Van der Waals model and the Beatty-Richmond model. We call them equations of state, but they are models for gas behavior, ever more sophisticated models. And we're relying on those models to help us explain what we see. Now, do you believe the models, the theory, or do you believe your data?
We don't know all the variables.
Your data is real. Whatever you see is real. In fact, Joule's experiment was real. He could not see a temperature change because he had a large amount of water, but it was real and it was explainable. You always trust your data. And to answer your question, Marion, that's what they did, which is still what we have to do today. We have to trust our data to be correct.
Until somebody can prove different.
No, the data is correct. Nature never lies to us. Now, there may be more subtle details that we don't see yet that someone may find later on. But what we find today, to the depth at which we're able to see it, is correct. Your experiment, assuming there's no experimental errors in it, which are correctable, that's the question you always have to ask. But your experiment is correct. Nature does not lie to you. They believe their evidence for the same reason we have to believe our evidence today. That's the nature of the way science is done. The theoretical explanations are models that are as good as we can make them be, but they are still models which probably are not complete or exact. The standard theory for subatomic nuclear physics turns out to be an exact theory as far as we know. The problem is you can calculate to 10 or 12 or 15 significant figures, and you can't measure that precisely. So the theory cannot be fully tested because we cannot measure precisely enough. And particularly, we cannot measure the masses and the decay roots of these subatomic particles precisely enough to fully test the standard theory. So the standard theory for nuclear physics remains the gold standard today. For our purposes in thermodynamics, I'm not sure there is a gold standard. As we'll see as we go further, that there is no equation that describes everything in thermodynamics. The basic reason is that intermolecular interactions are too difficult to describe mathematically. Or if I were to give you an equation that describes everything in thermodynamics, it would be pages long, because I would have to have all of those terms to describe in detail the ways that atoms and molecules can interact with each other. And no one has ever done that because it's not worth the effort to do it. There are better ways that we'll get in, and we've done a lot of data analysis, right? Using pretty sophisticated tools. Well, some of them have used sophisticated tools, Solver. Others still don't seem to have learned how to use it yet. But we use sophisticated tools to analyze data. We can still do that, and we can get results that we can begin to interpret. But we do not have an equation that describes the interactions of atoms and molecules thermodynamically with great precision. We do not have a gold standard in thermodynamics like they do in some nuclear physics. It's been a long time talking about that to answer Marion's question, but I think it may have been worthwhile. I hope you get a little bit better understanding of how science works as what? Science as an activity works. It's not what we're seeing in the lab and we teach in the class. The doings of scientific research are a little bit different than we see in our classrooms. And it's useful to understand that too, even though it's not internal pressure. What we'd like to have for the internal pressure is actually a function that we could evaluate. There is a quick and dirty way for doing things